Yeah, good evening, everyone. Hello, it's Harish. I am a PMRF student at ISA Mohali, and I'm going to conduct this sixth live interaction session for the course Introduction to Rings and Fields. So let me just share my screen. Before sharing the screen, Muthu, I discussed assignment number 4 in the last session. So if you want, then I can quickly revise what I did there, maybe in the first 10 to 15 minutes, and then we can discuss assignment number 5.
Because the last week I was not able to enter.
Yeah, there was some issue, but I have uploaded the recordings and notes is also there. So let me just share last week's notes first, and I will quickly say what I did there, and then maybe we can start the solution of 5th assignment. Okay. So let me go to the okay, this is not the file. This is not the file. It's opening. It's still not there. Can you see? Okay, so this is what we discussed last week. So assignment number 4. The first question says choose all the correct statements, and the first option is if R is a finite integral domain, then R contains exactly one maximal ideal, right? So in lectures we have already seen that a finite integral domain is always a field, and a field has just two ideals, 0 and the entire field, and so there is only one maximal ideal, 0. That's the 0 ideal there. 0 ideal there is a maximal ideal, and that's the only ideal. So the first statement is correct, that if R is a finite integral domain, then R contains exactly one maximal ideal. Now, what about the second statement? Suppose that a ring R contains exactly one maximal ideal, then R is a finite ring. So it's like a converse of the first statement. So if R has exactly one maximal ideal, can you say that R is a finite ring? Not necessarily be an integral domain, but whether the ring is finite or not. So do you want to put any comment on it, Muthu?
It's okay. We will start today's class.
Okay, so you don't want me to revise this?
I will go through. I will go through it.
Okay, okay. So let me just so now you might be seeing the blank page or the previous one. Muthu, you are able to see the new page, right?
Yes, board is there. I
Okay,
can able to see the board.
okay, okay, okay. Now let me just start writing. Okay. So it's our sixth meeting. So, and we are going to discuss assignment 5 in it. Let me just copy paste the first question. In getting head. Let's see. Yes. So first statement is first question is choose all the correct statements, and the notation for Z is it's the ring of integers, and R denotes the field of real numbers. So considering those notations, you are supposed to answer these four options, whether it's correct or not. So the first option says let fx be any non-constant polynomial. Then the ideal generated by fx in the ring of polynomial ring over integers is contained in only finitely many maximal ideals. And the second option is just a counter statement to the first one, which says that the ideals generated by a polynomial in the ring of polynomial ring over integer is contained in infinitely many maximal ideals. So definitely one of them is correct. So I'm just going to give an ideal that would be contained in infinitely many ideals, and so the second option is going to be correct and the first one is not. So if you have any example, then you can say, otherwise I will just state what the example I have come up with. So the example is to consider this polynomial fx is equal to x minus 1, then the ideal say I is equal to ideal generated by x minus 1 is contained in the ideals generated by x minus 1 and p, where p is a prime number. And not only that, so it's a small check that the ideals x minus 1 p, where p is a prime integer, are maximal ideals of zx. And as so you have infinitely many ideals which contains this polynomial x, the ideal generated by this polynomial x minus 1. Thus the statement A is false and B is true. Okay. So this implies A is false and B is true. Okay. Now the third statement is to see the same thing, almost the same thing over the ring, polynomial ring over the reals. That if fx is a polynomial in the polynomial ring over reals of degree 2, then that ideal generated by fx in Rx is contained in exactly 2 maximal ideals. And the fourth statement says that it is contained in at most 2 maximal ideals. So let us just see which statement is correct. So the first C statement says that the number of maximal ideals that it contains is exactly 2, means it cannot be contained in one maximal ideal or say more than 2 maximal ideal. So for that we have an counter example. So if we take the ideal generated by fx to be the maximal ideal itself, then it would be contained in exactly one maximal ideal, that is itself. So what I want to say that for part C, take fx to be just x square plus 1, then the ideal generated by fx is maximal. Is maximal in Rx. So if it is maximal, then it cannot be contained in any other ideal, proper ideal. So the only maximal ideal that contains it is itself, right? So it is contained in exactly one maximal ideal, that is itself. So the statement turns out to be false. Okay. Now second says that it's going for any polynomial, the ideal generated by fx is contained in at most two maximal ideal. So even this example doesn't contradict the D part, and we are going to show that the D statement is actually the correct statement. So for that, what we are going to do, so we are going to use here that if K is a field, then Kx is a PID. Okay. That statement I hope you are familiar with. So we know that if K is a field, then Kx is a PID, principal ideal domain, and a PID is just an integral domain in which every ideal is principal, means it is generated by just a single element. So now since R is a field, so Rx is going to be a PID. Thus Rx is a principal ideal domain. So how it is going to help us, let's see. So let fx be a polynomial in Rx and I be an ideal in Rx such that the ideal generated by fx is contained inside I. Not just ideal, we want here maximal ideal, right? So since we are in principal ideal domain, then this ideal I is also principal, and thus it has to be generated by a single polynomial. So that's what we are going to use, since Rx is a principal ideal domain, therefore I is a principal ideal. Let Gx belongs to Rx be such that I is generated by Gx. Then since fx is inside the ideal generated by Gx, and fx has degree 2, therefore degree of Gx has to be less than equal to 2, because fx contained in Gx, that implies that this implies gx divides fx, right? And since fx has degree 2, therefore the degree of gx has to be less than equal to 2. Now if let us consider case by case.
Excuse me,
What?
fx is a polynomial of degree 2.
Yes.
Therefore, it can have maximum of 2 irreducible factors.
Yes.
So the ideal generated by an irreducible factor is the maximal ideal.
Yes.
So therefore, ideal generated by f of x is contained in the one of the irreducible polynomial factor, the ideal generated by that factor.
Yes. Yes.
So therefore, you can have maximum of 2 maximal ideals which contains ideal generated by f of x.
Yes. Yes. That's precisely the idea. Okay.
Is it okay?
Yes. Yes. It is okay. The only point is you. So you need to see the same thing over gx. If it's not a principal ideal, then there might be problems, because then there might be maximal ideals that contains like factors of fx. Yeah, if it is generated by more than one element, then there might be a problem. That the same problem was happening over zx. But once you have that each ideal is a principal ideal, then if fx is contained in gx, then gx is just a factor of fx. Now you can just reduce your problem to the factors of fx. That's what I'm saying, that gx divides fx, and since it's now just we will conclude the argument and see what are possible maximal ideals based on the degree of gx. Okay. So first thing is definitely if degree of gx is 0, then ideal generated by gx is equal to entire R, because then it becomes a non-zero constant. And since not just R, but it's Rx, so in this case, gx is not maximal. So this case is not going to happen. Second case is when you have degree of gx to be equal to 1, then gx is equal to say x plus b, where a, b are from the ring. And as you said, since fx can have at most 2 linear factors, therefore gx can have at most 2 possibilities. Okay, so there are 2 possibilities in this case. And what if gx has degree 2? So degree of gx is equal to 2, then fx is also a degree 2 polynomial, gx is also a degree 2 polynomial. So gx is nothing but some c times fx. I should say, since fx is contained in the ideal generated by this, and fx is some c times gx for some c in r star. Okay. But then this implies fx time c inverse is gx. So that's like obvious thing. If nothing to, because you are in a field, so this will be like c inverse fx is gx, and thus the ideal generated by gx is also contained inside the ideal generated by fx. Thus both these ideals are same. And this implies that there is only one possibility. One maximal ideal containing fx in this case. And if gx is a degree 2 polynomial and like fx is a degree 2 polynomial which is giving you a maximal ideal, so then like it cannot be factorized further and to give a maximum, to give maximal ideals, means this case and this case are totally exclusive. There won't be any intersection in that. So in this case you have at most two possibilities, and here you have one possibility. And in the above case you have zero possibilities, because that won't give you a maximal ideal. So there are at most two possibilities that can hold. Thus your statement D is correct. Okay. So this is a true statement. Okay. Okay, then let's have a look at it. Till then I will just copy paste the question to okay. Let's move to the next question. So it says which of the following rings are PIDs. Again, the notations are same. Z denotes the ring of integers and R denotes the ring of field of real numbers. So that is something already we have seen number of times, and in the lectures also. This question is like a repetitive question. So
Z is a principal ideal domain. It is an integral domain, and every ideal is principal ideal.
yes, every ideal is a principal ideal. So yes, so Z
So A is true.
is a PID. So that we have already seen. What about the second one?
Second one, every field is a principal ideal domain, because
Yes.
every field has only two ideals generated by
Yes.
0 and 1.
Yes. R is a PID since every field is a PID. Yes. What about the third one?
Third one is a counter example that every is a UFD, but it is not PID.
So very good. So this third one has already been discussed in the class, that ZX is not a PID, so that is discussed in lectures. What ideal you can give as an example, which is not principal?
In ZX,
Yes. That ideal means we have seen a number of times in the lectures. So the ideal generated by 2 comma x. This is not principal. Okay. You understood why it's not principal?
because you cannot find a single element.
Yeah, but what should be the argument for that?
2 comma x.
Yes, but means what's the problem with this ideal? Say if it is generated by some single element, that what contradiction you will have?
Because
So, so you can look at this like in this way. So if it is generated by a single element, and then 2 and x has to be written as a multiple of that single element. Thus, the degree of that single element has to be strictly less than 2. So either it's a degree 1 polynomial or a constant polynomial, right? But if it is a constant polynomial, then you as it is, so it has to be an even integer, because 2 just let me just, so what I want to say, so if it is, say it is generated by a single element, say fx, then first of all fx must have degree strictly less than 2. So it's going to be linear either a linear polynomial ax plus b or a constant polynomial. If it's a linear polynomial, then you can say that 2 won't be there inside fx, because you will have multiples of ax plus b inside it, and 2 cannot be written as a multiple of that. So this option is also not possible. So only thing is, this ideal 2 comma x has to be generated by a constant polynomial, right? But there also, like, you have problem, because say you pick
x
your constant, yeah, you pick your constant to be, say, alpha. So here only the polynomials that you have are just alpha times fx, where fx is from uh, rx,
ZX.
sorry, zx. So you have only that kind of polynomial, but you have x here, right? So x does not belongs to alpha fx unless your alpha is 1 or minus 1. But if alpha is 1 or minus 1, then that's a unit, and that will generate the entire uh, uh, zx,
The whole ring.
the whole ring. But 2 comma x is not the whole ring. So that's a problem. Okay. Anyway, this is already been discussed in the lectures also, and I have also given you the idea about it. So that's why 2 comma x is not principal. Uh, so zx is not a principal ideal domain. Now, what about this Rx comma y?
R is a field,
Yes.
and any R x1, x2, xn n greater than or equal to 2 is not a PID.
Yes. And you can get to the contradiction to the same argument. Instead of 2, in place of 2 comma x, you just replace it by x comma y.
X
Okay.
comma y.
You will and then follow the same idea. It's not going to be a PID. So it's not a PID. That has already been discussed in lectures also, and the same idea will work here also. Ideal that will create the problem is and these are not the only ideals that are not principal. There are many more ideals, but we just giving one is enough. So this is not principal. Okay. So I hope the second question is also clear. So let's move to the third one. Yes. So it says which of the following rings are UFTs? The notations are like the previous ones. So R is an integral domain. So whether an integral domain is a UFT or not.
Which of the following rings are UFTs? So the first one is false.
Yes. And you can see that the counter example is already there in one of the option.
That is
Yes.
Z of square root of -5.
Yes. So Z root of square root of -5 is an integral domain. But it is not a UFT. And the reason behind it is, can you say why?
You can find that square 6 can be written in two different ways.
Yes, yes, yes. So one thing is clear, right? That it's a Noetherian ring. So Z minus root of 5 is a Noetherian ring. So for a Noetherian ring, the factorization at least exists. Okay. Factorization. Or I should say finite factorization exists. But the problem that we will have is the uniqueness. Okay. But 6 can be written as 2.3 and also
Is it a square root of -5?
yes. Thank you. So it's root of -5. So 1 plus root of -5, and then you have 1 minus root of -5. And you can see that these two are irreducibles. And here also these two elements are irreducible. And for unique factorization, you also need to see that they are not associates. So 1 plus also 1 plus root of -5 is not associate to 2 and 3. So like for it, they are two distinct factorization. They are not factorization up to associates. So thus this implies that 6 has two distinct
So we have to mention that they are not associates also, right?
yeah, because if they are associates, then it will be considered as the same factorization. So that part is also crucial. But that is, I think that should not be a problem, because you can use the norm argument, something like that. 1 plus root of -5, if you have multiplied with some unit, then like to check that 2 is not associated to this, if you say 2 dot some u, where u is the unit, is 1 plus root of -5, then you take the square both sides after sending -1 here, and then you continue like that, you will come to a contradiction. It's not difficult to see that they are not associates. Because you can see this ring as a like the same kind of calculation we have in the class we have done for a plus eta b kind of elements inside the ring of Gaussian integers. Now 1 plus root, this is like root of 1 plus root 5i. So this root 5 is not going to play much role. Only this eta you have to remove, and for that you need to take the square, and then the things will get managed easily. So by the same argument, you can say that 2 is not associated to 1 plus root of -5, and same 3 is not associated to that. Okay, so 6 has so 6 doesn't have a unique factorization. Doesn't has unique factorization. Doesn't have unique factorization. This implies this is not a UFT. Okay. So third option is not correct. A and third are not correct. So A and C are false. What about the B one? ZI?
R is a field.
Yeah, R is a field.
Therefore, any field adjoint with the X is a UFD.
Yeah, or you can just say this, if a ring is UFT, then R of X is also UFT, and since your real numbers is a UFT, then Rx is a UFT. Yes, you're right. Okay. And what about the B option? Ring of Gaussian integers?
ZI is UFD.
What's the argument behind it? So for B part, you just need to check this is in fact a PID. And how you can prove that? So let I be I'm just giving some hint. It's not a complete proof, but it is somehow complete. So let I be an ideal in uh, in Zi, non-zero ideal. Okay. So take X inside I to be such that norm of X is minimum in I, minimum among the elements of I. And what I mean by this norm, so this is
A squared plus B squared.
yes. So this is just the modulus of X considered as an element of C, because Zi is contained in C, so you just take it as an element of C and you have to just take the modulus of it. So you just look at the X which has the minimum modulus among the elements of I and show that
I is generated by that element.
Yes, X will generate the entire ideal. So in this way, like you can conclude that this is a PID, and once it is a PID, you know that all PIDs are UFTs. Okay, that's also not difficult to see. So also each PID is a UFT. And for that also, like it's a two-step process. So PID implies Noetherian Noetherian ring, and for Noetherian ring, the finite factorization exists because for UFD you have a condition that if the ascending chain of principal ideal stabilizes, then the factorization exists. That's the proposition covered in the class. So if you have Noetherian ring, then each ascending chain stabilizes. So in particularly the ascending chain of principal ideals stabilizes. Thus, each Noetherian ring has factorization, finite factorization. So finite factorization, of course, exists. Okay, then use the proposition position the following proposition. So proposition says this has already been proved in class that let R be an integral domain in which factorization exists. So as it's a PID, so factorization exists, that is already been guaranteed, in which factorization exists. Then R is a UFT if and only if every irreducible element is a prime element. So and this property is also true when you have PIDs, right? Just a minute. So, Sunita, your video is on, so maybe you can turn off it. Okay, so every irreducible element is a prime element, and that is true for PIDs. So there is no issue in that also. Thus, each PID is a UFT. So, and in the first part, we saw that Zi is the ring of Gaussian integer is a PID. Thus, it's also a UFT. So B is true. Okay. Now, fourth one, D part you have already said that as R is a UFT and Rx is also going to be a UFT. That is already seen in the lectures. So the fourth one is also correct. D part says since R is a field, therefore R is a UFT, and this implies Rx is a UFT, and that is, since for any ring, if R is a UFT, then Rx is a UFT. Okay, so D is a true statement. Okay, so is there any doubt, or I should move to the next part, next question? Okay, so let me move to the next question, which says, which of the given elements are irreducible in the given rings? Yes, first two seems to be easy.
253 is a composite number.
Yes, it's the composite number.
23 into 11.
23 to 11. Good. So as Z is a PID, so here irreducible, therefore in Z irreducible and prime elements are same. So Sunita, your video is on. If you want, you can just turn off your video. Okay, thank you. So irreducibility and being prime is the same in Z. So as you said, 253 is a composite number here. It's just 11 times 23. So thus 253 is not a prime, and hence it's not a irreducible element. Yes. What about the second one? 530 inside ZI.
Yes.
So what's the irreducible element? First of all, it's not zero, not a unit, and then if it can be written as a product of two elements, then one of them has to be a unit. So if you can write an element as a product of two elements, which are not, neither of them is a unit, then that element is not irreducible. So can you see 530 is irreducible or not?
530 cannot be expressed as sum of squares of two integers.
Sum of squares of two integers. But why you need that for irreducibility?
Because you can factorize 530 in ZI
Yes, that is okay, right? So 530 is factorizable in Zi, means it is not irreducible, right? So
Not
530 you can,
irreducible.
yes, 530 you can
Is
simply write as 2 times 265. Now this is definitely not a unit, and 2 is not a unit, 265 is not a unit, because we already know the units in Zi are just 1, -1, eta, and minus of eta. So it's factorizable, right? So it's not a irreducible element. Now, what about the third part? Whether it's an irreducible element in QX.
irreducible.
It's irreducible. Yes. Because
So first degree.
say if what's the argument, Puthu? So if it can be written as a product of two polynomials, then one of them must be of degree 1, another must be a constant. Yes.
We can say non-zero constant.
Yes, non-zero constant. Suddenly, like, yes, other must be a non-zero constant.
Non-zero constant is a unit.
Non-zero constant is a unit. So this implies, say, or I can just write it here on itself. That's the unit in QX. Thus, you cannot factorize it in terms of two non-units. So it is irreducible. in Q of X. Yes. What about the fourth one?
It is factorizable with integer coefficients.
The fourth one?
2x minus 1 into 4x plus 5.
Yes. So it is factorizable as integer coefficients. So D is 8x square 6x plus 5, right? 6s minus 5, you can write it as 4x plus 5 and 2x minus 1. Therefore, it is not irreducible. It is not irreducible in ZX. Okay. So that's it. These are the first four questions. So if it is okay, then let me move to the fifth one. If you have any doubt in those, you can just ask me. Okay. So silence means it is clear. Let us move to the next question. So I'm just copying other three options. Yeah. So it says choose all the correct statements. First one is if R is a Noetherian ring, then Rx is also a Noetherian ring.
This is a Hilbert basis theorem.
Yes. So that's a Hilbert basis theorem. So it's going to be correct. So A is precisely the Hilbert basis theorem. Covered in lecture. Okay. What about the second one? If R is a PID, S is a subring of R, then S is a PID. Whatever you need to answer this part B, we have already seen in the class. This lecture, not just the class, but also in this session also we have seen. Even if you are not following the lectures and if you are there in this interaction session, then you can answer part B.
ZI
What? ZI.
is a PID.
Yes. And what subring of it you are considering? So first of all, what you believe that the statement is true or false?
I think it is false.
You think it's false. So you should come up with a counter example, right? So what are the PIDs that we have seen in today's session? And what are the non-PIDs that we have seen? So instead of thinking of R, think of S first. But what ring you have seen that is not a PID?
Every field is a PID.
Yeah. I think if you try to think of this S, then R you can definitely think. First, try to think of a ring that is not a PID, and we have seen such a ring in today's discussion. Yes. So, what example you know for a ring that is not a PID?
Not a PID. R of X, Y, not a PID.
Yes. What else? Very
Z of
close.
X is not a PID.
Yes. So Z of X is not a PID. So do you know a PID that contains Z of X?
So the Z of X, S is also Z of X, R is also Z of X.
No, then the statement is true. It's not a counter example, right? We want a counter example.
Yes. ZX is Noetherian.
So try to think of a ring that contains Z of X, but it's a PID. One such we have already seen in above options. Yes. Instead of Z, if I replace it with some nice ring, then whether Rx is a PID, polynomial ring is a PID.
You mean R is a ring of fields.
Yeah, if you replace it with a field, then Rx is a PID, right? Now try to embed ZX.
Any field with the X is a PID.
It's a PID. ZX is not a PID. Then what choice of ring you can take? Now it is like everything I have said. Yes. Just tell me quickly what choice of R you can take.
R is R of X and Z is Z of X. Yes is Z of X.
Yes, take R to be Rx and S to be
Z of X.
Z of X. Then we have seen that R is a PID, but S is not a PID. Okay, so the statement is, so this is false and this one is true. And the third one we have already proved, right? In the every PID is a UFD that we have already proved above. This is true. And this we have already proved in the beginning.
S is not a PID. We have to conclude S is.
So that we know now that the ideal generated by 2 comma x is not a principal ideal. That also we have seen in the beginning, right?
Yes. Now in the counter example, R is PID, S is a subring of R.
But S is not a PID, right?
But we have to tell S is not Noetherian.
No, we just need to prove S is not PID.
S is not PID.
That we already seen that S is ZX is not a PID because you consider the ideal generated by 2 comma x. Noetherian is a weaker statement that every ideal is finitely generated. PID is stronger.
But in the original question, then S is a Noetherian, not PID.
What original question?
Question B, if R is a PID and S is a subring of R, then S is Noetherian. That is what is.
Then S is a PID.
S is PID.
Yes.
But in the original question paper, it is given S is Noetherian.
Original question paper, it is given S is Noetherian. Is it? Then there might be like some typo there because the solution that I have received is for this question that S is a PID.
So please kindly, I will also check because what I have written is S is Noetherian.
So if that is the case, then you can mail them and ask for a clarification. Just write it over the discussion forum, and then if that is the case, then there might be a typo. Let me just open the website and see what.
We can easily check assignment 5.
Yeah,
How I have written S is Noetherian.
With week 5, assignment 5. It's opening. If it is Noetherian, then I think it should be true. Because every PID is a Noetherian ring and subring of a Noetherian ring should be Noetherian. No, it's also there in the assignment also. If R is a PID and S is a subring of R, then S is a PID.
So in the original question also it is only PID.
Yeah, it is only PID.
Okay, thank you.
Okay. Okay. So third part we have already seen. What about the converse of the third part?
That ZX.
Yes. ZX is a
UFT, but not FPAD.
ZX is a UFT, but not a PID. So this statement is clearly false. Okay. Okay. So with this, we are done with the fifth question. Now let's move on to the sixth one. So it's again the same thing. You have to correct the, you have to choose the correct statements. The notions are the standard notations. So the first question is, a greatest common divisor of 3, 4 in Zi is 1.
3 and 4 are relatively prime.
They are relatively prime in Z, and the question is asking you about Gaussian integers. Something that are relatively prime in the lower ring, they might not remain relatively prime in the uh, higher ring. But that's also, in this case, it is true. But we have to prove this taking elements inside Zi. Okay. So let A plus eta B belongs to Zi be a common divisor of 3 and 4. Then what happens? Then there exists C plus eta D and say E plus eta F inside Zi such that A plus eta B times C plus eta D is equal to 3 and A plus eta B times E plus eta F is equal to 4. Now, you take the complex conjugation and then modulus. So this will implies A plus eta B modulus square times C plus eta D modulus square is equal to 9, and same here, A plus eta B modulus square E plus eta F modulus square is equal to 16. And this will implies, this is what, this is A square plus B square times C square plus D square is equal to 9, and A square plus B square and this E square plus F square is equal to 16. And this implies, first of all, a square plus b square is a positive integer because a and b are integers, so a square plus b square is going to be a positive integer. It cannot be 0 as well, and it divides both 9 and 16. So positive integer that divides both 9 and 16. So definitely this implies a square b square belongs to natural number, and a square plus b square divides the GCD of 6 and 19, and the GCD is nothing but 1. So what is the possibility for a square b square? A square plus b square has to be 1, right? And this implies either a is equal to 0 and b is equal to plus minus 1, or a is equal to plus minus 1 and b is equal to 0. Now, if a is equal to 0 and b is equal to plus minus 1, this implies a plus iota b is nothing but iota or minus iota, because b is 1 or minus 1, a is 0, and this gives you a plus iota b is plus minus 1. So all these are, this implies a plus iota b is a unit. So there is no common divisor of non-unit common divisor of 3 and 4. So only units divides 3 and 4. That's why the greatest common divisor that divide 3 and 4 is 1. Okay, so this implies GCD of 3 and 4 is 1. Okay. Now what about this? The second question.
For both polynomials, sum of the coefficients equal to 0.
Yes.
Therefore, x plus 1 is a factor for both.
X plus 1 is a factor for both. But in x plus 1 itself, the sum of coefficient is non-zero. So if x plus 1 is a factor for both, then minus 1 is a root. For this, definitely x plus 1 is a factor. So here also, if x plus 1 is a factor, then minus 1 is a root. But here you will get 2 plus
when
2.
When sum of the coefficients 0 means,
yes, you are right. And but that is not enough. You also need to check that minus 1 is not a factor of this. Right?
I think both minus 1 and plus 1 are not factors of the 8th degree polynomial.
This is always true.
For x squared minus 1, the roots are 1 and minus 1.
Yes. For this 8-degree polynomial, yes, -1 is
Neither
not
of
a
them is a root.
neither of them is a root of this polynomial.
Yes. -1 is not a root.
-1 is not a root. But what about, yeah, -1 is not a root. That's why x plus 1 is not a factor, right?
Yes, yes,
The other one is a factor. 1 is a
yes.
root, right? So
Both 1 and -1.
let me just write it.
X plus 1 does not divide the first polynomial.
Yes, x plus 1 does not divide the first polynomial. So for B, the polynomial is, let me just write, fx is 2x 2 x raised to 8 plus 2 x raised to 4 minus 5x cubed plus 1. And your gx is x square minus 1. So f of -1, if you put, then it's going to be 2 plus 2 plus 5 plus 1 not equal to 0. Therefore, x plus 1 is not a factor of fx, right? But f of 1 is 2 plus 2 minus 5 plus 1, that is equal to 0. Therefore, x minus 1 is a factor of fx. And what does this implies? This implies the GCD of fx and gx is x minus 1, not x plus 1. So the statement is false. Right? Now, what about the third one? Two x square plus 1. So this
2x squared
polynomial,
plus 1 is a factor of the 5th degree polynomial.
yes. That's why the GCD is going to be 2x square plus 1. We will just see it by the long division. Only thing we have to ensure that the coefficients are inside Q. That won't be a problem. So we take fx to be 2x square plus 1, and gx is, just see, it is 2x raised to 5 minus 10x4 plus 3x cubed minus 15x square plus x minus 5. Let's just divide gx by 5 fx. So you have 2x squared plus 1 here, and 2x raised to 5 minus 10x4 plus 3x cubed minus 15x square plus x minus 5 here. So highest degree terms you have to divide. So it will be x cubed 2x square, when you divide 2x5 by 2x square, this is going to be x cube, and multiply this x cube with 2x square plus 1, we will get 2x5 plus x cube, and then you have to change the sign. This will get cancelled and this will get cancelled. What you will get? You will get minus of 10x4 minus 15x cube, 15x square plus x minus 5. Then again divide the highest order term, minus 10 square x square by 2x square. You will get minus of 5x square, and multiply this minus of 5x square with the entire polynomial. You will get minus of 10x4 minus of 5x square. Change the sign. This is plus, this is plus. We will get minus 10x square plus x minus 5. Something I am missing or what? X cube. Oh, I did small mistake here. So it should be 2x cube should also come here, right? Because after subtracting 3x cube, x cube from 3x cube, we should get 2x cube, and then minus 15x square plus x minus 5. And then minus 5x square will come here. And it will become 2x cube plus 10x square minus 5 of x square minus 10x square plus x minus 5. And then again divide the highest order term, 2x cube by 2x square, you will get plus x. Yes. It will be 2x cube plus x, then we have minus and minus. It will be subtracted, and we have minus of 10x square minus 5. Highest order term, divide, then gives you minus 5, and then you have minus 10x square minus 5, and subtracting, you will get 0. So thus fx is a factor of gx. This implies 2x square plus 1 divides 2x raised to 5 minus 10x4 plus 3x cube minus 15x square, 3x cube minus 15x square, and plus x minus 5 in qx. Okay, as you can see, this polynomial is definitely inside qx, so there is no doubt in that. Okay, so the GCD is going to be then fx. So this implies GCD of fx and gx is nothing but fx, which is 2x square But in the question you have that the GCD is 1. So the original statement is false. Okay. Now, what about the last statement? The greatest common divisor of x minus 2 and x4 minus 7x squared plus 11x minus 10 in the polynomial ring over complex numbers is x minus 2. So checking this is easy.
X equal to 2 is a factor of that polynomial, fourth degree polynomial.
Yes. So since x equal to 2 is a factor of the second polynomial, so it's going to be x minus 2 is going to be a factor, and then thus the GCD is nothing but x minus 2. Yes, we are correct. So let me just write it. So D, for the D part, our fx is x minus 2, gx is x4 minus 7x square plus 11x minus 10. Okay, and you can see that g of 2, which is nothing but 16 minus 7 into 4 plus 11 into 2 minus 10 is 16 minus 28 plus 22 minus 10. So that is 38 minus 38, which is nothing but 0. So this implies x minus 2 is a factor of gx, which is nothing but your fx, and thus GCD of x minus 2 and x raised to 4 minus 7x squared plus 11x minus 10 is x minus 2. So this is true, right? Okay, so with this, the solution set is completed. If you have any doubt in any of the part, any of the question, then you can ask. We still have time left. So Muthu, if you want, then
Will you explain what is the primitive pth roots of unity where p is the prime number? So that primitive pth roots. Otherwise, you can explain to us in the next class also. No problem.
so primitive root of unity means, so the roots of unity forms a group, right? Under multiplication.
Yes.
So the primitive root means the root that is also a generator of that group.
So the set of all nth roots of unity. So here we have to take a prime number. Set of all pth roots of unity form a group under multiplication.
Yes.
Where the generator will be cos 2 pi by n plus I sin 2 pi by n. That we take it as omega.
Say for example, you consider p to be 3.
P to be 3. Okay. 1 omega squared.
Yes. So the
Omega
generator is
mm.
omega is a generator of that group, and omega square is also a generator of that group.
So it is a generator.
Yeah. So the generator.
What about omega squared is also a generator. Omega squared power 3 is 1. Omega squared power 2 is. So omega squared is also a generator. So both omega and omega squared are generators. So both are primitive. Third roots.
Yes, third roots of unity.
So that means 3 is a prime number. Like that, in general, if P is a prime number, except one, all other roots are generators of the group. Is it okay?
I think so. Because the roots of unity forms a cyclic group, and in a cyclic group, everything is a generator, right? If like the cyclic group is if you take the cyclic group of order P, and every non-trivial non-identity element is a generator, right? Inside Z mod PZ, every non-trivial element is a generator.
No, that is true only for prime number.
Yes, that is true only for prime number.
If we take the fourth roots of unity, which is not so. Only I and minus I are generators.
I and minus I are generators. But the definition of primitive root is this only, that you inside the group of roots, all roots, the multiplicative group of all roots, the generating elements are the primitive roots of unity. Let me just verify it. I think that's the definition. So this is there in any of the assignment, or?
Yes, yes, it is there. But it was not dealt in the video lecture, I think.
Okay. Yeah, so one definition is an nth root of unity is said to be primitive if it is not an mth root of unity for some smaller m. So that precisely means that n is the smallest number such that say alpha of n is equal to 1. So that you understand, right? It also means that it's going to be the generator. Its order is same as the order of the group. Right? So one definition is, and say you.
That is what is that is clear. That is the set of all nth roots of unity form a group. Any generator of that group, it is a cyclic group, and therefore any generator is called primitive nth roots of unity. Yes. Now the other one you said relating to things.
So say so what the other definition says. So something is a nth root of primitive nth root of unity if it is not an mth root of unity where m is strictly less than n.
So primitive nth roots means it should not be primitive mth root of that unity.
It should not be a root for a smaller m.
Smaller.
That also means that its order in the group generated by the roots is not less than the order of the group, right?
Okay, they are equivalent.
So they are equivalent. So both kind of definitions people use and both are equivalent. So there is no problem in that. So what question, can you say the exact statement of the question? Maybe then I can understand the context of it in better way.
I will give the what is the term? So primitive pth root they are denoting by this symbol zeta p, zeta suffix p.
Okay.
Zeta.
So which assignment is 7 or 8?
This assignment number 7.
Okay, so which question?
Question number 5.
So I opened it, the 7th one. When is the due date? 15 March. Okay. So I can't tell you the solution, but definitely these things I can let you know. So fifth question. Okay. So PQ are distinct prime numbers and CP and CQ denotes any primitive pth and qth root of unity. Denote the field of rational numbers. Choose all the correct statements. Yeah, here I think it means the same, that it's the generator of the group of all roots of unity.
Because they say that Z5 is not a member of Q of C7.
Which part it is?
No, in general,
Okay.
the primitive fifth root of unity is not a member of Q of the smallest field containing Q and seventh root of primitive seventh root of unity.
So now you can maybe you can relate it with the other equivalent definition that I gave you.
That is, you said for the primitive seventh root means any primitive seventh root is not a root of smaller.
See, in case of prime, this thing is very trivial because that form a cyclic group of order 7. So any element would have order dividing 7. So either its order is 1 or 7.
1 or 7.
So if it's not identity, then its order has to be 7. Then it cannot give you identity for a smaller number.
Okay, I will go through.
Okay. But the only point is here it is written less than equal to Q and then CP belongs to QCQ.
So it is definitely false.
I won't say anything.
Okay,
although I have said everything.
Because Z of 5 is not in Q of Z of 7. It is not valid when P less than or equal to Q.
I have said everything, but still I don't want to say anything.
Okay, it's all right.
It's all right now. Okay, so assignment 6, I think already the date is gone or still the
Yes,
date is
assignment 6 has gone.
It's gone, right? So what do you want me to discuss next time? Assignment 6 or some other questions?
I think assignment 6 is only in rings.
Okay.
We have 2 more classes.
Yes, we have 2 more classes.
2 more classes. And then we have in fields, we have 2 sessions are there. In field 8 and 9. Week 7 is field.
Week 8 is finite fields.
Yes.
So week 7's deadline is
coming Wednesday.
This Wednesday, right? So it would be gone till our next session, so that we can discuss.
6 and 7 we can discuss.
Both I won't be able to cover in one session.
Yes.
So maybe I can emphasize on the one, and the second I would discuss if I have time. So like what you want. 6 or 7. If I have time, then I will discuss something from the second one also. Otherwise, we will cover the one that you prefer.
Sir,
Yes.
week 3, will you discuss the week 3 assignment?
So which question you want me
Second
to?
problem, second question.
Let me just open the assignment. You have the question with you, right? Or
Yes,
you
I
want me
have.
to share? Okay. Second question says we have to choose the correct statement.
Yeah. Excel.
Like R and C denote the field of real and complex number respectively. So
Their edges onto homomorphism R over X comma Y to complex number system. Another option, their edges ring homomorphism complex number system to R.
yes.
Their edges ring homomorphism from complex number system to real number system to complex number system. So fourth one, their edges subject to ring homomorphism from real number system to complex number system. Can you explain with some examples, sir?
So the correct options is that there exists a surjective ring homomorphism from Rxy to C, and there exists a ring homomorphism from R to C.
To C.
So from R to C, it's like trivial. You can just embed R inside C.
Identity map.
Just identity map you can do.
How's the A bit, sir? A bit is true, no? On to homomorphism for R over X comma Y.
So both of them are field. So you can just see this question as like considering the kernels. So what are possible kernels? So for a ring homomorphism, the kernel is an ideal, right?
Okay.
And for a field, the possible ideals are just the entire ring and the zero ideal. Trivial ideal. So if it is the entire ring, then it has to be the zero morphism.
Okay.
Okay. So for part there exists a ring homomorphism from C to R. That should also be correct, no? If you, but yeah, zero homomorphism is not a ring homomorphism because phi of 1 has to be 1.
Yeah, phi of 1 to be 1. Yes.
So only possibility remains is the morphism that for which you have the kernel to be 0. That is injective homomorphism.
Okay.
For a field, the only ring homomorphism is the injective homomorphism. If the domain is a field.
Okay.
So that's why the option B is not correct because you cannot have an injective homomorphism from C to R.
Okay.
And then the fourth one says there exists a surjective homomorphism from R to C. So if there exists a surjective ring homomorphism from R to C, so then that has to be injective because we already know that the only ring homomorphism are injective. Are also injective, right?
Yes.
R is also a field. So the fourth option means if there exists a surjective ring homomorphism, then that is already an injective ring homomorphism, and that will imply R and C are isomorphic as rings. But that's not correct, right?
That's not correct, no?
They are even not isomorphic as groups, so they cannot be isomorphic as rings. So D part is not true because the only ring homomorphism for a field from a field are injective ring homomorphism, and if it's also demanding the surjectivity, that will imply the isomorphism is there, and R and C are not isomorphic. So D is not correct. B is also not correct, as I said that we cannot have an injective homomorphism from C to R, and A and B are correct. Sorry, A and C are correct.
A and C are correct. Okay.
A and C are correct.
Okay. Thank you, sir.
Okay. Yes. Any other doubt or anything? So Muthu, if you want, then we can start the next discussion from say week 7, and then if we have time, then we will move to week 6, because I think most of the things in week 6, at least the conceptual things we have already discussed. Only the Gauss lemma and identity and criteria is there.
It is okay.
Okay, Sunita, it's okay with you also?
Yes.
Like if we, okay, so we will
Yes,
start
sir.
by, okay, so we'll start discussing seventh assignment, and then if we have time, then we will see some problems
So
on the
one
sixth.
more bit, sir. Week 4 assignment.
Yes,
Fifth bit, sir. Fifth bit.
week 4 assignment. Fifth question.
Fifth problem, sir. Fifth problem. So we have
Okay.
taken a polynomial ring with infinite many variables. We have
Yes.
taken an ideal generated by x1 square, x2 square, so on. We have to do some correct statements here.
Yes, yes.
Can you explain about this, sir?
So the first two options are like, if I will show the second part is correct, and then the first one is of course not correct. So second
Yes,
part
sir.
says the ring R contains infinitely many maximal ideals. So you can take the ideals generated by, I think, x1 minus a, x2, x3, x4, so on. So that will, so you can take the ideals generated by x1 minus a is a real number, and then comma x2, comma x3, dot, so on. So it's a maximal ideal for any a inside the real number, and as the choices for a is varying over the entire ring of real number, so there are infinitely many choices.
Okay.
Okay.
Yes. Okay. Next,
So,
sir, quotient ring R over I contains exactly one maximal ideal or infinitely many maximal ideals. Among these two, which one will be correct, sir?
so it has the third one, that it has exactly one maximal ideal. So why is it so? So maximal ideals of R by I are in 1-1 correspondence with the maximal ideals of R.
Okay.
That contains this ideal I.
Okay.
Okay, so if you consider J to be a maximal ideal that contain I, then J is also a prime ideal, because every maximal ideal is a prime ideal.
Okay.
So if J contains I, then J contains xi squares for all I belongs to n. So what then, if as it contains xi squares, it also contains xi's because it's a prime ideal.
Yes, yes. X, right.
So J will contain all xi's for I belonging to 1 to n. Thus, J will contain x1, x2, so on to xn, every variable. So, and this ideal, so what does this mean? That J contains the ideals generated by x1, x2, x3, dot, so on. And the ideal x1, x2, dot is itself a maximal ideal.
Yes, sir. That is itself.
So if an ideal is containing another maximal ideal, then it has to be the same ideal, right?
Yes, yes. Both are.
Yeah. So there is only one possibility for J, that is the ideal generated by x1, x2, and so on.
Okay. So it will have only one maximal.
So only one possible ideal is there. So in the last discussion session, I discussed this entire assignment. So the entire solution is there. If you want to see, then you can see the notes also.
Okay.
And okay, so in the last session, I just did this assignment number 4.
Okay. Where will be the notes, sir? It will be mail, sir, or the solution will whatever sent by the NPTEL, in that they will be there, sir, solution.
It's there over the course web page. Like if you open the course web page on Swayam.
Oh, course web page. Okay.
Then in the last option is problem solving session.
Okay, problem.
So once you click there, then you will find a link for Google Sheet. And in
Okay.
that Google Sheet, you have the entire notes and the videos.
Okay, sir.
Okay,
Thank you,
so
sir.
just go there and see. Okay.
Okay, sir. Thank you, sir.
Okay. Okay, then, so I will stop here. See you in the next session. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay.